So if we can if we can move on to our final presenter this afternoon, who is Mick Prince, and Mick will be presenting on his title, which is Design and Evaluation of an Adjustable Trans-Radial Prosthetic Socket, which is appropriate for lower resource settings. Thanks, Mick.
Okay, hi everybody. So my name's Mick Prince and I'm a PhD student. And my research is on, as John said, the design and evaluation of an adjustable trans-radial prosthetic socket, which is appropriate for lower resource settings. And this, again, is part of the Fit for Purpose prosthetics project. So I'm going to do a quick review of some existing socket designs and then look at linking user needs and design parameters in a user-centered design process. Then identify some of the variables in designing and evaluating a socket and talk about some pilot work to look at some of those variables. So looking at existing socket designs, and this is probably the most common. This is known as a self-suspending socket because it doesn't need any additional components to keep it in place. And as you can see, there's a single structure which extends above and below the elbow, and I thought it might just be interesting for people who don't know how something like that is made. So the first step is to capture the shape of the residual limb, either with 3D scanning or in this case with plaster bandage. And then a copy of the limb is made out of plaster and key anatomical landmarks are transferred across in the process. And then the shape of that copy is changed by the prosthetist in a process called rectification. And this is where the prosthetist tries to target certain areas for loading and unload other areas. And once they're happy with the shape, the socket can either be made by draping a sheet of hot plastic over that shape, or in this case, by adding some layers of textile and then using vacuum to suck some resin through. And then when that all hardens, the socket can be trimmed and finished off. So that's a one-piece design. This is now a two-piece design made by, I think, the Red Cross. And here there's a separate component below the elbow cup, and above the elbow there's a cuff and some straps which provide the suspension. And then taking that idea maybe a bit further, if you have multiple components both above and below the elbow and open areas in between those, so for example struts and pads and straps joined together to form an open frame, then that can be adjustable both at the time of fitting and also on a day-to-day basis by the user. And it also increases the range of materials available for use. And thinking about materials, the example I've shown here is a textile-based socket, and this is the MIT, which is adjustable by the user by tightening or releasing cables using two adjusters, and so they can adjust the fit on their own arm. So that's some existing designs, and then thinking about how to place the user at the center of the process. So I started by looking at what the user needs are and what some of the key design parameters are, and then tried to link those together. And in some cases that's fairly obvious, so if it needs to be affordable, then the designer needs to keep the cost down. But to link them all together, I used a weighted design matrix, and that suggested that a good starting point would be an adjustable open frame device, because it can be fitted quickly, it can be adjusted by the user, it offers the option to use a range of materials, and that in turn should help with repair issues. And then also importantly, the open area will hopefully help with heat issues. So looking in a little bit more detail at one aspect of open frame design, the loading of the tissue interface. And so the characteristic with a socket is that there's a constant loading, an intrinsic loading generated just by putting the socket on. And then on top of that, there's activity loading due to moving or doing tasks, which is an intermittent load. And so I was interested in the relationship between tissue health and the magnitude and the duration of loading. And this has been characterized with a sigmoidal curve, so lower loads can be tolerated for longer. And it's important also to note that the distribution of those loads from the tissue interface down into the deeper tissue varies within anatomical sites on the subject and between subjects, and also varies over time. So it's a complex issue. Well, thinking about the open frame again, if the components interfacing with the tissue are the pads, then the average pressure under the pad will be the load divided by the area. But the way that that pressure is distributed is going to be governed by the cross-sectional profile of the pad. And it's important to try and avoid high pressure gradients, high normal pressure gradients, because they generate additional radial shear stresses, and that causes so-called edge effects. So I wondered if we could apply a chosen pressure distribution and capture the shape that the tissue is displaced to, would that be useful to inform pad design? And I did some preliminary tests, and this was just on my own arm with a very simple device, and that device needs to be improved before it's used for further testing, just to make sure that there's no risk of pinching or damaging the skin, and also just to make it more practical to use. But the basic idea is that the pressure at the base of a brass bar is a function of its length. So if you have an array of brass bars of different lengths, you can create a pressure distribution across the base of the array. And so I chose a pressure distribution to try, and made an array of 3mm square brass bars of lengths to suit, and put those in a frame which could be adjusted so that either the bars could slide relative to one another or they could be locked in place. And then, starting with that on a horizontal surface with the bars locked, I then put my arm in a position so the area of interest was horizontal, and then put the device on the arm, release the pins to apply the pressure distribution, and then locked it again to capture the displacement. And the main image there shows the different shapes which that generated at different areas around the circumference of my forearm, and the different shapes are due to the different surface stiffness in those different areas. So that's one way of doing part of the design, quite a specific example. But I'm also interested more generally in how to evaluate the socket as a whole, and this brings up the question of what is a good socket fit. And at the moment, the way I'm thinking about that is that it's a balance between functionality and the comfort or the tissue load and tissue health of the device. And the best fit or the optimum balance will differ between individuals, and probably the best gauge of if we're near to that optimum balance is going to be the real world use, which is something that Salford has done quite a lot of work on. But in terms of developing a new design and testing new ideas quickly, it'll be useful to have some proxy measures, and I've looked at quite a few, but at the moment I'm focusing on coupling. So that's how well the socket is linked to the underlying skeleton, how much it moves as the user intends, and gross tissue deformation. And I'm developing a scanner, 3D scanner based system to capture those two variables. I'm currently doing the validation work on that. But I've done some pilot work on an anatomically intact arm using a test socket which doesn't really look much like a socket at all. It's some pads mounted on a quite a simple adjustable frame. Well, there isn't really much data out there like this, and so I do want to include existing socket designs in the studies as well to get some benchmark values. But just to give an idea of the kind of information I'm trying to obtain, so this is one way of looking at it. And here there's a scan of the bare arm, and then superimposed on top of that, the blue frame shows the pose of the socket in relation to the arm. And then there's also a force vector, which is the weight of the socket. And then in this case, there's also an additional external loading vector. And so you can calculate the moments and the loads and how that changes. And then going a step further, you can compare if you apply or if you change the loading, how does the socket move? And in this case, the blue frame was the original position, and then an external load was applied. And in the top right image there, you can see that the main effect that that had was to cause a rotation along the long axis of the arm, and the red frame is the new position that external load caused the socket to rotate to. And that is, I think, all I've got time for today, but thank you very much indeed.
Thanks very much, Mick. We're going to move on to John now for the last minute that we have.
Better make this brief, hadn't I? Mick, I could think of 100 questions, I think, on trans-radial sockets, but I think one of the things that we've seen so far is the issue with socket fit, haven't we? And I mean, ideally, what are you looking for in terms of your design, and how do you think it's going to help the sort of situations that we've discussed in the previous presentations in terms of getting socket fits correct and easier for people in these lower middle income countries to be able to use and to wear? What do you think the key aspects are that you're trying to find?
I guess material availability is one. I mean, this is why I'm interested in the open frame. The fact that it potentially, I mean, Kenneth's doing fantastic work on trying to improve that supply chain, but if it was possible to be less dependent on specific materials, I think that could help. And then in terms of fit, if you could try and either embody some of that fitting expertise which you prosthetists have, if you could try and embody somehow that in either fitting tools or in the device itself, and as part of that maybe have that adjustable component, so that people, if it doesn't feel comfortable, they don't have to try and travel back a long way to gain expert clinician input, that they can actually make some adjustments themselves to make the fit more comfortable on a day-to-day basis. And so some way of achieving that, those seem to be the key factors to me.
Absolutely. Well, look, thanks very much for that. And as I say, I'm sorry we don't have more time for your questions on your presentation, but I am aware of time. It is very, very slightly just after 4.